Today I was asked to speak about introduction to history and philosophy of quantum computing, and that is actually in my case on the background of work I must say for decades represented in this book. In the 80s, a book on the philosophy and foundations of quantum mechanics, and my book on quantum computer, from the quantum world to artificial intelligence, and then this book on artificial intelligence, when do machines take over, with now in the second German and English edition, and also a Chinese edition. Now, on that background, I will speak in the first part about history and epistemic foundations of the quantum world, and then we will consider mathematical and physical foundations of quantum computing and quantum communication. And in the end, there will be an outlook to quantum AI, and that will be the link to my second talk tomorrow about machine learning. Now let's start with the history and epistemic foundations of the quantum world. And perhaps you know, quantum mechanics is founded on deep principles which are in the end confirmed and illustrated by experiments. And here in the beginning, as a reminder for you, the wave-particle dualism illustrated in the double slit experiment. Here in the first picture, a quantum system, for example, an elementary particle such as an electron, is neither a classical body with uniquely predictable location on the screen, for example, footballs which are shot in the direction of a wall with two splits, and behind this wall there is a screen with the distribution of these hits of the balls. Nor it can be considered as a classical wave with constant invariance pattern behind the double slit. And if someone interprets the situation with a classical view, that means in the sense that the electrons are considered as classical balls, for example, then you are enforced to believe that the ball is passing simultaneously the double slit. And that would be puzzling for you. That's a famous cartoon to illustrate that, such as the non-classical skier here is puzzling for the classical observer, and splitting up here the traces with the tree. The tree here in the cartoon illustrates more or less a double slit. So in the classical world, in classical physics, you assume that the state of a classical particle of a ball, for example, determined by location and momentum, can be measured with simultaneously both components, the momentum and the location, with increasing accuracy. And under that assumption, you get the mathematical idealization of a line which is illustrated here for the classical path of a particle. But actually, as I mentioned before, a particle follows all possible paths simultaneously. You must sum up them here in the integral of Feynman. So in the end, the quantum state is characterized by a probability distribution. And that is closely connected with the famous Heisenberg uncertainty relation, which was formulated for the first time 1927. by Heisenberg, and that means again location and momentum of a quantum system cannot be measured simultaneously with arbitrary accuracy. If you start to measure location with more and more accuracy, then momentum starts to scatter and vice versa, and that all depends on the ultimately smallest unit in the quantum world, and that is Planck's constant. Heisenberg, by the way, was not only a great theoretical physicist and a philosopher and a Nobel Prize winner. Heisenberg was a brilliant mathematician. And therefore, in this time, in the 20s, he was well aware what was going on simultaneously in mathematics, namely the emergence of the new algebra, which is connected with names in mathematics such as Emmy Noether, Hermann Weyl, and so on and so on. And therefore, exactly 100 years ago, in 1925, in summertime, on his holiday, on the nice island in Helgoland, in the North Sea of Germany, Heisenberg formulated the first paper for mathematization of quantum mechanics. And in this paper, he interpreted for the first time the distribution of the states not by a real number, that is the tradition of classical physics, but by a matrix. That means the abstract mathematical object concerning these different states. And later on, these matrices were represented by operators on the Hilbert space, and I will come back to that later on. Now, anyway, Heisenberg was in Munich, born in Bavaria, and his great competitor in that time was Erwin Schrödinger. He was an Austrian. And he considered and interpreted a quantum state, it seems to be in a quite different way, namely as a wave, probabilistic wave. And you know, waves can be superposed. And that is the background of a famous thought experiment in that time in 1935, namely to consider the state of a system as a wave state which can be superposed. And that is illustrated here with this famous example of a cat which is caught in a closed box together with a radium preparation, and that is a quantum system which can decay by random, and by this a hammer mechanism is initiated which can destroy a bottle with hydrocyanic acid, and then the cat is killed. But as long as the box is closed, with equal probability, the cat is dead and alive. So in order to interpret the situation in the Schrödinger sense, you have to consider the whole box as a quantum system, and to measure the quantum system is here interpreted by opening the box. And that means, in the interpretation of Heisenberg, the superposition of these waves states now collapse instantaneously, and then by observing, the cat is either dead and alive. And that was discussed here in the 80s in this book we edited, and in that book later on there were famous contributors, for example Anton Zeilinger and Peter Mittelstädt. He was the last habilitant of Heisenberg, and by the way, he cooperated with the Italian group of quantum logic in Florence since the 70s and 80s, I think, especially with Marie-Louisa dalla Chiara, and there is a former student, Roberto Giontilli, and he was, Peter Mittelstädt was a supervisor. We know of your work. Now, anyway, this year, 35, was crucial for the epistemic discussion in that time of the foundations of quantum mechanics. Because in that year, another famous principle was discovered, namely entanglement. And that was by Einstein himself. Here in the picture, you get an impression how intensive and emotional even the discussion in that time was. Here on the left, you see Niels Bohr. He was the head in Copenhagen of these young quantum physicists in that time, and on the right, Einstein, the representative of the classical view. And in classical physics, two bodies far away can always be determined completely and independently from one another, even if they are in far distance. And that is called this point of view locality. And Einstein, and then in such a situation, of course, an effect in the classical world needs some time, the transfer of a signal, which is limited by the velocity of light, following relativity theory. But Einstein was puzzled because the formalism of the quantum mechanics seemed to suggest that a situation is possible where far distant objects can be connected by instantaneous signals, and that seemed to violate the classical principle in relativistic theory, which I mentioned before, as the limit of the velocity of light. From a quantum physical point of view, there are no different objects in a far distant position, and there is no violation to the signal transfer because they are in a common state, although they are in far distance, and that situation is called a non-local interpretation of this kind of state. Anyway, the question was, is reality local or non-local? And that needs at first a mathematical formalization. And on the right here, it's a picture of John Bell, a famous theoretical physicist from CERN, and he especially formalized the situation, the consequence on the Einsteinian assumption of local reality in the so-called Bell inequality. And on the left, you see Alain Aspect. He was head of a research group in Paris who did the experiments. Now, the situation illustrated is the following. Here I use a somewhat different version of the Bell inequality, which I mentioned, the Clauser-Horner-Shimonis-Holt inequality. And the situation is illustrated here in that picture. At first, we assume a source of prepared photons, prepared in an entanglement that can technically be done, for example, by a nonlinear photonic crystal. And then it is assumed that the pairs of these photons, the photons are sent in opposite direction to these different filters here on the left and the right, and the filters are characterized by different settings, namely A and A stroke, and B and B stroke. And if a photon passes the filter, that is indicated by 1, and if the photon is reflected by 1. Now, in the Einstein interpretation, all these possible events are completely independent. That means locality, and therefore, under this assumption, you can collect all these possible independent events and describe it with classical statistics. And that is done here in that term, a combination of A, B. That means you can insert there the values 1 and -1 plus A stroke B plus A stroke B stroke minus A B stroke. And then it turns out by simple combination that in any case this term is between -2 and 2 in this interval. And that is illustrated here in the diagram, depending on the changing angles in the different settings. And it is assumed that the angle between A and B and A stroke and B stroke are equal. And then you have the prediction of the classical experiment, and then the quantum mechanical measurements were done, and it turned out, Aspe and others in the beginning of the 80s, that these quantum measurement violates the classical predictions significantly. That was the situation after the beginning of the 80s. And in that time, it's also historical, I was a young professor in Constance, University of Constance. And Constance is nearby to ETH Zurich. And at the ETH Zurich, in that time, there was a guest professor, Abner Shimony. He was a physicist and philosopher from Boston, and they invited me, and we organized a seminar on the foundations and the philosophy of quantum mechanics after the results of Alain Aspect in the beginning of the 80s. And that was very exciting, because all these famous names which I mentioned here, John Bell and Zeilinger and Klaus, for example, were invited there, and we were discussing. And I remember very well that Abner Shimony, the physicist and philosopher, he was always claiming, what are we doing here? We are doing, he said, experimental metaphysics. And the idea was physicists are now discussing deep philosophical questions in the philosophy of science and physics, which go back to the very beginning of science and philosophy with the pre-Socratic philosophers. And then the idea came up, is the reality local or non-local? That must be mathematized, and then it was decided. So in that sense, it's progress in this kind of understanding of philosophy. But it is not only impressing from a philosophical point of view, and that is the topic today. It is also the foundation of revolutionary technology such as quantum computing. I start here with a remembrance of a classical computer. The classical computer is deeply rooted in classical logic, proposition logic here, the connectives. You know that with the distribution of the truth values, and these truth values 0 and 1 can be interpreted as bits, and the distribution of bits then can be used technically to realize the gates, the classical gates, and this is a survey on classical gates, the classical logics, the Boolean algebra of these gates, with the NOT gates, the AND gate, the OR gate, the exclusive gate, or here's a swap gate, which exchange the input and the output, and the copy gate, and so on, and so on. And these gates can be combined, and by that we get to circuits, classical circuit. I like this simple example here of such a circuit because this is the situation of Leibniz. Technically, when Leibniz constructed his first classical mechanical computer, then he had the problem in the decimal system. If you add 9 plus 2, you get 11. Then you have a carrier, a decimal number for the next position of the decimal number. And Leibniz realized it by the clever idea of an intermediate gear wheel between the gear wheels which represents a decimal position. And here it is done in electrotechnology by the exclusive OR gate and the AND gate. And here, if you add at first 1 plus 1, then in the decimal, in the dual system, you get 1, 0. So you have a carry bit, in this case 1. That is realized here. 1 plus 1 with the exclusive OR gate delivers 0. And then these values for the AND gate delivers the carry bit 1. And so on. You can construct it. Frege, Gottlob Frege, was already aware that in logics, all the possibilities of connectives can be constructed by a distinguished set of connectives. And that has, of course, an advantage in technology, because then you only need some special gates, and then you can construct all the other possible gates in a classical quantum computer. Now let's change to the quantum world. And therefore we considered, for example, a photon as a quantum system. And here the quantum system can be polarize the photon in a vertical or horizontal way, for example. And there are other possibilities for realization with other elementary particles. But then with the idea of superposition in the quantum case, you can consider the intermediate state between 0 and 1. They are represented here by quantum bits in the familiar bracket notation. And you can consider the intermediate state when the quantum bit is more or less 0, with more or less probability 0 and 1. And that is indicated here in this notation by the coefficients representing these probabilistic weights. That is the old idea of Schrödinger. You remember the probabilistic interpretation. And of course, the superposition is the first crucial idea of a quantum computer. In a classical von Neumann computer, you have to calculate step after step all these bits. And then that needs a lot of time and energy. But here in the quantum computer, you can prepare the bits in a superposition state, and then the computational devices are applied to the whole superposition, and that leads to an enormous acceleration of computation. And by that calculations with the classical computer, which cannot be done during lifetime, they are now realized, and in perhaps minutes or seconds. For example, decoding of the of a large number, a code in banking, for example, by factorization, the famous quantum algorithm, Shor algorithm, which can do that. Now, this is an illustration of the possibilities of position, superposition. In the classical computer, there in the first line, by manipulating bits in gates, you can realize the application of a classical non-gate to this sequence of bits. But then in the quantum gate, it is in the superposition state, which I mentioned before. The application of the gate operation, the non-gate, provides psi stroke. That means with only one application of a gate operation, two manipulations are already realized. And in 2 qubits, 4 manipulations are already realized by only one gate operation on 2 bits. And in general, 2 to n manipulations are already realized by only one gate operation on n qubits. And now with the connection with the Heisenberg world, that means with the formalization, quantum formalization. That is illustrated here in the Bloch sphere. That means we consider a sphere with the 3 axes, x, y, and z. And here the extreme events of 0 and 1 are located here at the poles of the sphere. And then we can consider the immediate state, here illustrated by a pointer which is continuously rotating, here with more or less probability to be 0 and 1. And here at 3 o'clock, we have the superposition state with equal probability to be 0 and 1. Now, the rotating state vectors in the Bloch sphere correspond now in the quantum formalism to applications of unitary operators in quantum mechanics. And that is crucial by mathematics. And it fits exactly the physical situation. Unitary operators must be reversible. And you know, the classical logical operators, the classical logical connectives are in general not reversible. And in a quantum computer, they are realized by quantum gates. And we will now consider some examples of the quantum gates. First simple realization is the one-array operator for one-array qubit, the so-called X operator, which correspond to the classical NOT gates. And that is a situation, you remember the Bloch sphere with the extreme values at the poles. The pointer is jumping flip-flop from 0 to 1 and vice versa. And mathematically, it is described now in the Heisenberg world. That means with algebra. Very simple here. That means the operator is realized by a simple matrix, mechanics of matrices. The idea of Heisenberg, which is applied here to the quantum bit in the state 0. And simple calculation here leads to exactly 0, 1, flip-flop, and vice versa. And that is the symbol of this kind of gate. And there are other gates, Y operators, Z operators, describing the rotation around the Y-axis and Z-axis. And this is the operator for describing the rotation with this signature here. And now a very crucial operator, the so-called Hadamard operator. And again, you remember the operator is represented mathematically by a matrix. This is this matrix. And if you apply this matrix now to quantum bit 0 by simple calculation rules, to get the superposition state. And if you apply it to quantum bit in the state 1, it differs here by the sign minus, and this is the symbol of the symbol of the this quantum gate, and then you can go on to secondary operators for secondary qubits, and here the swap operator, I mentioned it in the beginning, which exchange the two inputs 0 and 1 in the output with this symbol here of the quantum gate, and the so-called controlled operator in the abbreviation C naught. And later on, it turned out, I will show you that this quantum gate can deliver entanglement. So we have the operators generating entanglement and superposition here with this sign. And that is my last example for today. A three-array operator, the so-called Toffoli operator, CC naught, that means with double control bits, X and Y here in the components, and the target bit here is this third combination. And in this case, the quantum bit corresponds to 2, 2, 3, because three components, 2 to 3 vector, that means an 8-dimensional vector here. And in my book, I introduce and considered, as elsewhere in these textbooks, the other possible operators. And I think that is sufficient at first to understand universality in the sense of what we considered in the classical case with the distinguished gates. You remember also here the Toffoli operator has a special role, because you can prove that each gate with two input bits and an output bit can be replaced by a certain number of Toffoli gates. In that sense, universal, and especially for practical application importance. Now that is, yeah. Yeah. I know that. Therefore, I mentioned these special examples with the two bits, and that I highlighted. And that is sufficient to understand what a quantum computer is. That is an architecture of the quantum computer with different layers from left to right. And in the first layer, the qubits are prepared with up and down arrows representing the alternative bit states. And then, very crucial, in the second layer, there are the application of the Hadamard operator. And remember, the Hadamard operator generates superposition, because we want to use the advantages of the acceleration of computing with superposition. So at first translated into superpositions. And then in the next layer, all the other operators and corresponding quantum gates are realized, which are necessary to construct a certain quantum algorithm. But the crucial point is, what you get in the end is a superposition. Again, you start with a superposition and you end with a superposition. And in the superposition, these possible solutions of the calculations are collected. But then we are in a situation such as in Schrödinger's cat experiments. Remember, the superposition must be measured, and measurement means collapse of the superposition in independent components with equal probability. Here the cat was dead or alive. That means the result of a quantum computation again is a superposition of all possible solutions, and that means in the Schrödinger interpretation they are weighted by the same probability amplitude, the wave interpretation. And now the task is to find an outreading algorithm in the superposition of the correct solution. And that means the quantum algorithm here must increase the quantity of probability amplitude of the correct solution and diminish the probability amplitude of all others. And the idea is the following. You have a certain set of elements represented by these numbers here, and then the unknown sort solution is denoted by x0, and then the idea is to apply an unknown so-called oracle function with the value 1 if the argument is x0, that means the thought element, or 0 in the other case. And the target is to find the solution x0, of course, in as few steps of application of the oracle function as possible. Now, if k elements are tested by the oracle function, the classical probability of finding the solution x0 is k divided by m, simply. And if the successful probability of finding x0 is denoted by p here, each classical algorithm needs p times n search steps. That means the number of search steps in the ordering of n, and n is the size of the whole data set. And that is, of course, a stupid situation, because you would lose all your advantage of quantum computing by superposition, because you have to test all these simple examples. Now, contrary to this classical approach, there are nowadays quantum algorithm, and the first example is the Grover algorithm, which needs less steps than in the ordering of sense. For example, the Grover algorithm, the square of the root of n search step, and that would mean at least a quadratic reduction. But actually, from a modern point of view, that has only didactical meaning. To illustrate it is possible to get improved solution time, because this quadratic reduction is still exponential. That means the algorithms is in the NP class. But nevertheless, by didactical reason, I will go a little bit in the details here. The Grover algorithm is represented by this kind of quantum circuit, and we consider at first a very simple case. The data set has only 4 elements, 2, 2, 2, with 2 qubits, and x input here with 2 quantum bit with 0 and 0 is here, and in the third channel there is the function value of our oracle function, which I mentioned before. And then you remember the architecture, which I demonstrated in general before, of a quantum computer. It starts at the second layer with the application of the Hadamard operator, because you want to get the advantages of quantum computing, and that is illustrated here. The input x, and this is y, x double qubit, and then by application to 0, 0, you get this kind of superposition here. And I mentioned it already, application of the Hadamard operator to quantum bit with 1, with this superposition result here. And then, of course, in the next step, we are eager. What about the oracle function? The oracle function must be applied, and we are in the context of quantum mechanics, and that means the oracle function must be represented by an operator. And that is UF here, the unitary transformation for the oracle function. And that means that the function value is uploaded into the qubit, the third channel there. I mentioned that before. And the state, that is now the crucial idea, the state remains unchanged in the case that this uploaded value is 0, but it changes in the case that it is 1. That means the sign is changing here of the concerned component, and we consider here the assumption that the solution x0 is 1, 0. That means here in the application case of the oracle function, we get there the change of the sign minus. This negative sign of component corresponds to a phase transition, and the phase difference here can be realized and transformed by an operator. The amplitude difference, the task is to diminish and to increase the concerned probabilistic amplitudes, and that can be realized by an transformation, again a unitary transformation. And in the simple case we are considering here with n equal to 2 qubits, we get the representation of this unitary transformation by this matrix here with the minus sign in for the diagonal values. Now, what is coming now is simple algebraic consideration, because this matrix can be decomposed in, so to say, smaller matrices. At the first step, we consider H to 2, H the Hadamard operation. This is a sign for the tensor product. The operators are separated, H multiplied with H, and you get this decomposition here with D stroke, a matrix in the center here. As a transformation, D corresponds to a controlled phase shift with a certain angle, and that corresponds to the minus sign of the coefficient of the concerned basis element. And then in the next step, this D stroke matrix is decomposed in further components here. Sigma means a so-called Pauli matrix, also more or less simple matrix, and twice these matrix we get a representation of the quantum NOT gate. And you get again this kind of decomposition here, and that this algebraic consideration consider no? correspond exactly to this circuit here, and you see again twice H on these two separated channels, therefore the tensor product, the separation, and here sigma x, a Pauli matrix, and here in the third case there is no gate applied in this second channel, therefore the identity operator, and that here's a controlled negation operator, and then in a mirrored way, as it was illustrated by the algebraic decomposition here, the what we considered here. The same situation. So algebra is the first approach, and then for the engineers, decomposition, and then representation in the gates. And so you get this circuit. Now, if you calculate this application of this matrix, you get the four-dimensional vector here, and which correspond to the qubit which we assumed, namely 0, 1. So that demonstrates here in this example that only one application of the oracle function leads to the result. And that is quite different to the classical situation, because in this case you need on average 2 1/4 search. On the average, therefore, quarter. That is a simple idea, because the solution being sought here then be found after the first, second, and the third search step, with each case with the same probability, 1/4. And if you sum up this possibility, then you get 2 1/4. That was a simplified case here for a 2-qubit and for x, and now in general for a n qubit. I will not go here in the details, but it meets, of course, the n+1 application of Hadamard gates, and that corresponds here to this expression here, summing up these possibilities of superpositions. And in the end, it turned out that in the general case, not only one application of the oracle function is sufficient, but you need what is nowadays called more of these application. That is the Grover iteration, so-called Grover iteration. And in the end, to make a long story short, the quantum algorithm performs the Grover iteration as long as the state of the register x, you remember x and y, the input is reached, in which a measurement delivers the result being sought, namely x0 with high probability. That is the architecture, and nowadays there are much better search outreading algorithms. For example, Fourier transformation. Perhaps some of you are here from electrotechnology, and in electrotechnology that is applied as a mathematical idea. It is applied, for example, if a non-period signal is decomposed in its simpler components represented by trigonometric mathematical expressions they represent, and here's the periodic cases. And that idea can be accelerated by so-called fast Fourier transformation by formulation in the digital case, and then in the end in the quantum version. And this kind of algorithm do it. They can realize nowadays the outreading task of superposition in an appropriate, realistic, technical, realistic way. Now that was, and you can illustrate that in the Grover formalism in a geometric way. I will not go here in the details. In the Bloch sphere, in the sense that you assume that the sought result x0 is projected here on one of these axes, and then the search pointer is approximating step by step the sought result, steps corresponding to the mentioned operators which are needed. Now that was superposition. Superposition in order to understand what is going on in a quantum computer from a mathematical point of view. And the mathematics is wonderful today more or less since the beginning of this century, and it is, of course, a great challenge nowadays to realize it technically. The next point here is quantum communication. And you remember the situation of entanglement. There are objects in far distant positions, and the entanglement in a non-local way. And the idea was, can we apply it to communication theory for sender and receiver now in far distant. And this discussion came up again in the 80s. I highlighted the 80s, and that was illustrated here in such a cartoon in the 80s. And you see we are in an old-fashioned world here with these old-fashioned phones. And the idea was to represent the sender and the receiver by Alice and Bob. They are communicating with one another. That was rather popular in that time. Here, Bob, who is mentioning, "Oh, Alice, you are the one for me," and Alice is whispering or thinking. But Bob, in a quantum world, how can we be sure? And on the blackboard in the background, there are the symbols of the so-called Bell states, which represent this kind of entanglement. Now, from a mathematical point of view, here the corresponding to combinations of several classical bits, for example, 0, 0, non 0, 1, 1, 0, and 1, 1. They correspond to entangled states for given combined quantum bits, which are mentioned there with equal probability for all partial states. And here are these examples for the so-called Bell states, psi plus minus and phi plus minus. And mathematically, that means entanglement. We understand what it means physically. But mathematically, it means now in the framework of Hilbert space, it means that the states are separated and the basis of the vector spaces are separated. It means they can mathematically, the combination only represent by tensor products. So in a mathematical meaning, entanglement means a factorization with tensor products is not possible, and that was proved by John Bell for these examples here. Sometimes it is believed that quantum communication can be used for instantaneous communication. But that is pity, that is not the case. Entanglement can only used for a common message of both proponents, sender and receiver, in a common superposition information. But what can be proved exactly is that the quantum communication can be used for absolutely secure communication. That has a lot of importance nowadays. Think of our military situation, for example, nowadays. And that is illustrated here in this simple example here. We imagine that Alice wants to send a message to Bob, and therefore they realized an entanglement between both. Alice is represented by the component A, this quantum bit A, Bob by B, and the entanglement AB here is this kind of entangled state. We know it is an entangled state because you remember it is one of Bell's state here, psi plus. And now that this entanglement is now realized here. This is a common source here for the photons, which I explained before. And then the task is that Alice wants to send a message psi to Bob. And how can we do that by entanglement? that is illustrated here in the corresponding circuit, quantum circuit. We have at first to consider that the entangled state here can be generated by application here to the input of the qubit in the state 0, 0 by application of the Hadamard operator, and there are separated channels. Here is actually no operator, therefore mathematically represented by the identity operator, and they are applied. And now the control NOT gate, which I mentioned before, and you remember my remark that the control NOT gate is able to generate an entangled state, and that is demonstrated here. That is a simple calculation that it generates P plus. And so entanglement is mathematically here represented, and now it must be connected with psi. That is a message which Alice wanted to send to Bob by application of the NOT operator here. And then the Hadamard operator should be applied in order to deliver all these possible messages which can be sent. And by simple calculation in algebra, you get this kind of expression, the superposition. Here, with 4 components which are indicated by these coefficients 0, 0, 0, 1, 1, 0, and 1, 1. And now that is a common superposition information which only is known to Alice and Bob. And now Alice wants to send the message alpha 0 plus beta 1, and therefore by a classical channel here, and classical means it can be observed by everyone because nobody can use it, this kind of key, only Bob and Alice. And then Bob getting this key, he knows, oh, she wants to send me this message. And if you consider the possibilities of 1, 0, or 0, 1 and 1, 1, you have to apply certain other more or less simple operators. Now, that is the illustration of what is possible in principle with quantum communication. Nowadays, there are a lot of discussions concerning the technical application here. The first discussion came up with Zeilinger in Vienna and his research group, and here with the far distant communication, and he had co-workers from China, and they are now the head of a very successful research group in China, and they are realizing it by satellites. That means far distance Earth stations which are entangled by satellites with the with photonic rays, and they are entangled. And so in the end, the idea is the vision to get a kind of quantum internet, and the quantum internet would deliver in some sense absolute security, because any attack elsewhere in this entangled world would instantaneously be registered and observed anywhere in this entangled world. And therefore the vision is to get a kind of quantum internet nowadays. Mathematically, that is again clear, and the possibility is proven, but technically it is a great challenge, especially concerning here far distant connections, and the repeaters, quantum repeaters and things like that must be realized and improved for that. So in the end, that's my last folie, in the end, in the future, quantum computer will process big data with superposition and quantum parallelism rapidly, and entangled quantum states, my last point, will open new avenues of distant communication in the quantum internet. And tomorrow, I will, at least in the last part of my talk, I will explain you how quantum neural networks in modern machine learning could be transformed into even something like artificial quantum brains with perspectives of machine learning and artificial intelligence. But my last sentence is the following. From a philosophical point of view, what I want to underline this morning is that in the beginning there is philosophy. In the beginning there were the pre-Socratic philosophers, the first physicists. They called themselves the first physicists. And then there was a long discussion in science and physics. And then the idea came up, local or non-local reality. And that must be mathematized. And that is then decided. You remember the idea experimental metaphysics. But that's not enough, because on that basis, in the end, revolutionary technology was possible. And that was the vision of your part here when you were a guest professor in this institution, namely to coordinate from a point of view of philosopher, of science, these philosophical, physical, and mathematical and engineering worlds. I thank you for your attention.